Alright, hello, and welcome to another episode of My Two Cent. As always, my name is Paul Emerson, and this episode is going to be about force of attraction and how it applies to our observation of gravitation, because there's a lot of information going around that gravity is a push. That gravity is a pull. No, I was correct the first time. The gravity is a push when in fact gravity is a pull. So what I want to do is I want to address why gravity is a pull, why gravity is not a push. So I'm going to be filming this a little bit differently. I'm not going to be filming myself speaking because science is about observation. So I'm going to start showing exactly why gravity is not a push. We're going to do this by using magnets again. I have two different sets of magnets this time. I know that magnetism is not gravitation. I understand that, but the behavior that you can observe is scientific. Observation is the fundamental principle of science. Without observation, there really is no science, so we can start there. What I want to start with, to get started with this, is I want to start with orientation, because we live in a geometric universe. There is a such thing as space because we experience space, but relativity says that space-time is physical, and that's not true. The physical aspect of space that they describe is only mathematical. It's basically based on mathematical principles and mathematical formulas that accurately describe the behavior that we observe. So the problem with that is that because the math shows us that there is a behavior that can be, because the math can show the behavior that we observe, we say that the math is stating that there is a physical component to the material aspect of space, but there's not. Space in itself is actually nothingness. I know that's hard to believe and hard to understand, but that's the truth. The reality is that when it comes to geometry of our universe, there is no actual space. All of the particles and everything holds all of the energy inside of them. And I'm going to illustrate this like this. We're going to say that this is a particle. Inside of this particle there is an electromagnetic force. There is a gravitational force, there is a strong nuclear force, there is a weak nuclear force, there is an inertial force, there is also a force for motion, there is a force for rotation, there is a force for it to remember its location. All of these forces exist inside of the particle. All of these forces interact with each other. M, L, and R. So gravitational force interacts with gravitational force. Electromagnetic forces interact with electromagnetic forces. Strong nuclear forces interact with strong nuclear forces. Weak nuclear forces interact with weak nuclear forces. They do this through our geometry. And that's one of the things that relativity describes. See, if you have two particles, particle A and particle B, and these particles have location and orientation because relativity is about observation. So you have this particle A at location A, and then you have particle B at location B. Sorry, I'm doing this off the top of my head, spur of the moment, so it may be a little confusing, but as I get better at this, my video presentations will get better. I like to do things more naturally and less planned out because I feel that it really conveys the information better, because I am limited and I can make mistakes. When you see my mistakes, you can learn through my mistakes as an actual added bonus to the learning process. So we have location A and location B. We have particle at location A, we have particle at location B. There's three locations in our space. There's an X coordinate, there's a Y coordinate, and there's a Z coordinate. There's an X coordinate, there's a Y coordinate, and there's a Z coordinate. These particles in our existence are located at these locations. So what you see on this sheet of paper is just two dimensions. There's if you know anything about the Cartesian plane, you have, I believe it's the y-axis and the x-axis. So the paper itself can be viewed the same way. This is the y-axis, this is the x-axis. So you're seeing the actual geometry. If I had a ruler, I don't, sorry. You can clearly see how these objects have a distance between them. The distance between them is how you know that they have location. That's how you know that they're taking up space. Matter, this is object C, cannot occupy the same space. So this is how math works. I can draw a particle. I can say this particle is located at coordinate 0, x, coordinate y, 0, and coordinate z, 0 on a Cartesian plane. Okay? I can draw another particle here. Now you can clearly see that the geometry between these two particles is different on the paper, but the math can tell you that this particle is also located at coordinate x, this particle is also located at coordinate y, and this particle is also located at coordinate z. I can show you this behavior with the math. The math is telling you that the location of these two particles is in the same exact location. But we know that matter cannot occupy the same space. So two particles of matter cannot occupy the same location. That means that only one particle of matter can be located at one space at one time. Now, because objects are in motion at any given moment in time, which is what relativity describes as the fourth dimension, is time, a particle can be located at coordinate x, 0, coordinate y, 0, and coordinate z, 0 at any moment in time. And then it can move to a new location, and another particle, particle B, can occupy that location at a different time. So that's how we have motion and orientation. That's what is important about space-time and relativity and understanding the behaviors and the interactions. Gravitation acts through space, but doesn't act on space. Electromagnetism acts through space, but doesn't act on space. There is no space. There's only the indirect observation that comes from understanding the behavior of matter itself. When you look at yourself and you look at an individual next to you, you see each other through space. But that doesn't make space actually relative. Space itself is not anything more than an abstract axiom. It has no material aspect to it. There is no physical aspect to space. And that is what I'm trying to address before I can get into the force of attraction. Because we have to understand that aspect first before we can even address how gravity is a pull and not a push. So what we're going to do. I'm going to show you orientation. Orientation is important because you can't accurately describe or understand gravitational interactions or influences if you do not understand orientation. The biggest problem that people have with believing that gravity is a pull instead of a push is that they lack a fundamental understanding in orientation. This is going to be a body of mass, and it's going to carry a mass attraction. The reason why it's carrying a mass attraction and not a gravitational attraction, the reason why matter is described as having a mass attraction and not being influenced by gravity directly is because scientists were smart enough to know that matter doesn't 100% necessarily have to be influenced by gravitation. Even though that is what we observe, that does not necessarily have to be to the absolute truth in the universe, because our observation of the universe is limited to our location on Earth. So scientists were wise enough to know that claiming that matter was gravitational was basically, we say that matter has mass attraction and mass attraction is gravitation. The reason why we say that is because we don't want to say that matter has gravitational attraction. We don't want matter to be limited to being a gravitational influence. See, a subatomic particle has a mass attraction and an electromagnetic attraction. A neutron has no electromagnetic attraction. It has no electromagnetic influence, but it has a mass influence. A photon is described as not having a mass attraction, but it has a gravitational influence. And see, this is where the actual observation gets in the way, because when you start describing things on paper and start explaining the behaviors that you see, you get confused with what is said by what is factual. And you have to make sure that your understandings line up with what you actually observe. So when you're talking about gravitation as a push, what you're saying is this mass will influence this mass as a push. This would describe a push, because the force of attraction itself is going to be in the direction away from the source, which is the center of the mass. So this object will move in a direction away from the mass. I think the reason why people draw the conclusion that gravitation is a push is because we can observe pushes easily. It's very easy for me as an individual to push an object. It's very easy for me as an individual to grab and pull an object, and I can understand the orientation. The problem is that when it comes to interactions, force interactions, you can't see them. See, it's the same exact illustration as the paper. You can clearly see that the magnet is being pushed by the influence.